Hey, it's No Way Audio, and today we're going to talk about how sound waves form and how they travel through the air. Let's get started. Every sound starts with movement. When you apply energy to an object, like knocking on a door or plucking a guitar string, you set it in motion and it starts to vibrate. That means the object rapidly moves back and forth around a resting position. This movement pushes and pulls on the surrounding air molecules. Those molecules pick up the vibration pattern and begin to oscillate back and forth around their own equilibrium point. That starts a chain reaction, because once a molecule is pushed, it pushes on its neighbors, and those neighbors will then push on their neighbors in turn, and so on. The result is a pressure wave, alternating regions of compression and rarefaction. In other words, areas where molecules are crowded together and areas where they're spread farther apart. And here's the key idea. A sound wave is just energy being passed from particle to particle. Each molecule only oscillates around its resting spot. It doesn't travel with the wave. What moves forward is the energy, not the molecules themselves. That's also why space is silent, because sound needs a medium. If there are no particles, like in space, there's nothing to pass the vibration along. The speed of sound also depends on the medium. In air, at room temperature, sound travels at about 343 meters per second. In water, it's faster, and in solids, it's faster still. Because the closer the particles are packed together, the quicker the energy can be passed along. A good example of this is the sound of a train. You can hear it coming through the rails long before you hear it in the air. So the speed of sound tells us how fast the wave travels through a medium. But be careful, do not confuse that with frequency. Frequency is the part of sound we hear as pitch. It means the number of vibration cycles a molecule completes per second and is measured in hertz. The faster the vibration of the object, the faster the molecules oscillate, and the higher the frequency of the sound. A 100 Hz sound vibrates 100 times per second, and a 1000 Hz sound vibrates 1000 times per second. Humans can usually hear from about 20 Hz to 20,000 Hz, though the upper range gets lower with age. And now let's talk about loudness. Sound pressure, measured in pascals, describes the size of the pressure changes. In other words, how far the molecules swing from the resting point. The bigger the swing, the louder the sound. The smaller the swing, the quieter it is. And it's important to note that sound pressure is always measured relative to the surrounding atmospheric pressure. At sea level, that atmospheric pressure sits at about 100,000 pascals, which is a lot, because sound waves we hear only change it by the tiniest fraction. For example, a jet engine might only add or subtract a few single pascals from the baseline, yet that's already enough to be deafening. But here's the challenge. The range of pressure changes humans can hear is enormous, far too wide to work with in plain pascals. That's why we use the decibel scale to make things easier to compare. 0 decibels is the quietest sound most humans can detect. Around 120 decibels is the point where sound becomes painful. And of course, a sound's loudness isn't a static thing. The farther it travels, the quieter it gets. That's because the same amount of energy has to spread over more and more surface area. If you double your distance from the source, the sound level drops by about 6 decibels of pressure. But loudness and pitch do not tell the whole story. The shape of vibration also matters. Think about it. If sound is just air being moved around, why doesn't everything you hear sound the same? Because every object has its own unique way of vibrating. An object's material, its size and shape, the way it's supported, and even the way it's set into motion all determine its unique vibration pattern, its sonic fingerprint. Imagine two lines, representing the vibrating edges of two objects. One moves smoothly, while the other one has a small bump in the middle. They both complete one full cycle of vibration from left to right and back again in the same amount of time, but the way they move is slightly different. This difference is the fingerprint, and it's passed on to the surrounding air molecules and then carried out in the pressure wave they create. When we record that movement over time, it also shows up in the waveform. And that's why you can instantly tell one instrument from another, even when they play the same note at the exact same loudness. A piano and a guitar vibrate differently, leading to each having their own distinct character. So yes, Every sound is just air being moved around, but the way it's moved makes all the difference. And that's it for today. If you learned something, make sure to like and subscribe, and see you next time.